Hi guys, Audrey here. So today we're going to do a few L'Hopital's rule problems that start off with the case of 0 over 0. All right, so let's get started. We're going to do limit as x approaches 0 of sine x minus x over e to the x minus e to the negative x minus 2x. All right, so the first thing that we always do is plug in. So sine of 0 is 0. So I get 0 minus 0, e to the 0 is 1. So I get 1 minus 0. So this gives me 0 over 0. And when we have 0 over 0, we are allowed to use L'Hopital's rule. So equals, we'll put a little HR on top to show that we're using L'Hopital's rule for yourself and for me, your teacher. And then we will apply L'Hopital's rule. So we want to do the derivative of the top divided by the derivative of the bottom. We're not doing a quotient rule here. We're doing derivative of top, derivative of bottom. So first, the derivative of sine is cosine x, and the derivative of x is 1. Divided by the derivative of e to the x is just e to the x. However, for the derivative of e to the negative x, we have a chain rule. So it's going to be plus e to the negative x and then minus 2. Just to make sure we get that, the derivative of e to the negative x prime, so the derivative of e to the negative x, that's e to the negative x. My chain rule tells me I need to then multiply by the derivative of negative x. So this becomes e to the negative x times negative 1. So that negative cancels out with the negative right here and becomes plus e to the negative 2x. All right, now we plug in again. Cosine of 0 is 1. So here I get 1 minus 1 over 1 plus 1 minus 2, which guess what? Gives me 0 over 0 again. So this is still our indeterminate form. Normally, before immediately applying L'Hopital's rule, we would simplify, except there's really not much simplification to be done here. So I'm just going to immediately apply L'Hopital's rule equals L'Hopital's rule HR on the top, limit as x approaches 0. The derivative of cosine x is negative sine x. The derivative of e to the x is e to the x minus e to the negative x because of the derivative that we just took down there. And now we're going to plug in again. Sine of 0 is 0. I have 1 minus 1 on the bottom. So I actually end up with 0 over 0 again. And again, there's really not much simplification that I can do here. So we're going to do L'Hopital's rule one more time. Hopefully one more is going to be enough. So equals L'Hopital's rule. The limit as x approaches 0, derivative of sine is cosine. So I'm going to have negative cosine x over e to the x plus e to the negative x. Again, we refer back to the derivative of e to the negative x that we just did right there. And now when I plug in, I end up with a negative 1 on top, a 1 plus 1 on the bottom, and I get negative 1/2. For our final answer, we no longer have L'Hopital's rule. We are done. Okay, for our next L'Hopital's rule 0 over 0 problem, we're going to do the limit as x approaches 0 of ln of 1 plus x minus tangent x divided by x squared. Same as before, the first thing we want to do is plug in. So I get ln 1 minus tangent of 0 is 0 over 0 squared, where guess what? Ln of 1, also 0. So I do end up with 0 over 0. So I'm going to apply L'Hopital's rule. And I end up with the limit as x approaches 0, the derivative of ln of 1 plus x is 1 over 1 plus x. We have a 1 on the top because the derivative of 1 plus x is just 1. So we either do the derivative of 1 plus x divided by 1 plus x, resulting in 1 over 1 plus x. The derivative of tangent x is secant squared x. So minus secant squared x divided by 2x. Now, typically before we apply L'Hopital's rule again, or really before doing anything, we want to simplify. So simplification is to either eliminate the necessity of L'Hopital's rule or to make L'Hopital's rule simpler. If I think about this problem right here, that 1 over 1 plus x turns this into a complex fraction. In other words, I have a fraction inside of a fraction. So I might want to get rid of that complex fraction. But if I do, I will have secant squared x times x plus 1, which would give me a product rule there. And then I'd have 2x times x plus 1, which would either result in a product rule or something that I would have to expand. So simplifying in this case would actually result in a more challenging problem. I'm just going to show you briefly what it would look like if we get rid of the complex fraction. We would multiply both the top and the bottom by x plus 1 to say 1 minus x plus 1 times secant squared x divided by 2x times x plus 1. Now, I don't know about for you, but for me, it seems like it will be easier to take the derivative from the original form than from this new form. So we're just going to plug in. I get 1 over 1 minus secant squared of 0 is 1 over 0, resulting in 0 over 0. Let's just double check why secant squared of 0 is 1. Secant squared 0, we're going to use our trig identity, is the same thing as 1 over cosine squared 0. Well, cosine of 0 is just 1. So we end up with a 1 there. Cosine of 0, you can plug into your calculators to see that it's 1. So here we get 0 over 0. We want to apply L'Hopital's rule again. Actually, I'm going to go down to the bottom to do that to make sure that I have space. So this is equal to HR on top, the limit as x approaches 0 of negative 1 over 1 plus x squared minus 2 secant x tangent x, all divided by 2. Okay, let's just take a look at those derivatives for a second. So the derivative of 1 over x plus 1 is the same thing as x plus 1 to the negative 1, which means I can pull that negative 1 down, have x plus 1, subtract 1 to the negative 2, and then multiply by the derivative of the inside, which in this case is just 1. So that's where my negative 1 over x plus 1 squared came from. Now let's think about the derivative of secant squared x. This is the same thing as secant x squared. In other words, I can move that 2 to the end to see that what I'm applying here is actually a chain rule version of our power rule. So I'm bringing the 2 down, I don't touch what's inside, I subtract 1, and then I multiply by the derivative of secant, which is secant x tangent x. So that's where that 2 secant x tangent x came from. Well, now what I see is that my denominator is just 2. So clearly it's not going to give me a 0, so I'm just going to straight up plug in. So when I plug in 0 here, I have negative 1 over 1 plus 0 squared minus 2. We just said that secant 0 is 1 times 1. Tangent of 0 we know to be 0 over 2, which results in a negative 1/2 for my final answer. There we go, we're done. So this problem was a little more challenging because the derivatives that we had to take were a little bit more challenging. Also, we had to think about whether or not it was worth it to simplify. I want to go back and talk about that again for just a second. So we said we didn't simplify because looking at the simplified form, when we were to get rid of the complex fraction, looked like it would be more challenging to take the derivative. Well, now we can notice another reason that maybe not simplifying was a good idea. Because when I look at this version right here, what I see is that the denominator is 2x. And one more derivative will cause that denominator to just become 2. Why is that useful? The answer is that when the denominator becomes 2, there's no longer a chance of it being 0. So we're no longer going to have the indeterminate form 0 over 0 because we'll have a 2 in the denominator. So we can see that by not simplifying, by just doing L'Hopital's rule one more time, we're already going to be done with L'Hopital's rule. We're not going to have to do it a third time because we'll have a 2 left over in the denominator. So one more derivative will cause the denominator become 2, eliminating the possibility of 0 over 0. And now we're just going to do one more problem. Okay, so for our last problem, we have limit x goes to 0, e to the x squared minus 1 over 1 minus cosine x, more trig, yay. Actually just realized that all 3 of these problems have the limit as x approaches 0. Other limits will also give L'Hopital's rule, will also result in L'Hopital's rule, will also result in the indeterminate form 0 over 0. It does not just have to be x approaches 0, so don't think that. Okay, so let's plug in. E to the 0 is 1, minus 1, that's 0. 1 minus cosine of 0 is 1, so that's just 0 over 0. Let's apply L'Hopital's rule. So we'll have the limit as x approaches 0. We're going to need to do a chain rule here. So the chain rule tells me e to the x squared times 2x. Derivative of 1 is 0, so that's 0. Divided by derivative of 1, 0, minus cosine x, so that gives me a plus sine x. So that 2x on top, because that's the derivative of x squared. So here we're just doing a chain rule. E to the x squared prime is e to the x squared times the derivative of x squared is equal to e to the x squared times 2x. Now we plug in again. No simplification to do here. I get a 0 on top because there's an x. Anything times 0 is 0. So e to the 0 times 2 times 0. Sine of 0 is also just 0. So equals, we can immediately apply L'Hopital's rule again. The limit as x approaches 0, well, I have e to the x squared times 2x on top. That means I'm going to need a product rule. So I'm going to actually go down and do the product rule before I write the integral. E to the x squared times 2x prime. So I can think of that e to the x squared as my f, and the 2x is my g. So this is e to the x squared prime times 2x plus e to the x squared times 2x prime gives me e to the x squared times 2x plus e to the x squared times 2, which results in 4x squared e to the x squared plus 2 e to the x squared. So we just did our product rule there. So we're going to replace our numerator there. Divided by the derivative of sine is cosine x. Okay, let's plug in again. I mean, there's really not much simplification I can do aside from factoring out e to the x squared, which is really not necessary. So we're going to get that this equals to 4 times 0, that's a 0, times e to the 0, 0, plus 2 e to the 0 over cosine 0, which gives me 2 over 1, which gives me 2 for my final answer after 2 applications of L'Hopital's rule. And with that, we are done. So that is all that we will be doing for L'Hopital's rule 0 over 0. I hope this was helpful. Bye, guys.